My name is Inigo Montoya. You kill my
functor.
Prepare to die.
Welcome to a Programming Languages virtual meetup pre-recording. My name is Connor Hoekstra, and we have finished the structure and interpretation of computer programs, which means we are moving on to our next textbook, which is going to be Category Theory for Programmers by Bartosz Milewski. So your first question might be, why are we covering CTFP? And the answer is that we voted over the course of the last three meetings of finishing up the structure and interpretation of computer programs. So if you've been watching these videos since the start of the structure and interpretation of computer programs, you might be familiar with this slide where I showed a plethora of books that we might be covering over the next few years. And we've added a few to this list of books, but we've checked off the top left corner, structure interpretation of computer programs. We're doing category theory for programmers right now, and the ones highlighted in pink are other books that were highly voted on. So we will probably be doing those in the future. And if you want to weigh in on what books we're covering, we usually hold those votes at the end of each of the book cycles. So if you'd like to vote on the next book, stay tuned until the end of this book. So what is the goal of the Programming Languages virtual meetup? I'm going to burn through this quickly because I covered this in the first meeting of the structure interpretation of computer programs coverage. We're going to work through books on programming languages together in order to grow our knowledge of programming languages and programming language principles, design, and implementation. And ultimately, this will hopefully give us the ability to write code that is more readable and expressive, maintainable and scalable, and beautiful and idiomatic, all things that I care deeply about. The format, it varies from meetup to meetup. It's usually running at about 1.5 hours per week on Mondays at 8 p.m. Eastern Time. The link to the meetup page will be in the description of this YouTube video. I said at the beginning of the structure interpretation of computer programs meetings that I was going to aim on 15-minute presentations. It typically more ends up being like 60 minutes of presentation and discussion back and forth. So it's usually 30 minutes of presentation, 30 minutes of discussion. For this book, though, the chapters are shorter, so I am going to aim at shorter presentations around the 15-minute mark to increase the amount of discussion, which is always the best part. So 45 minutes of discussion, and typically we try and wrap up at the 60-minute mark, but then usually folks hang around for another 30 minutes just to talk about what they're interested in terms of programming language and the stuff they've been learning about recently. So as I did for the structure and interpretation of computer programs, I'm going to be uploading these pre-recordings. Some people have asked, can I record the meetups? At this point, that's a little bit too much work. I would prefer just to pre-record these presentations. And for those that are in a time zone that doesn't line up well with 8 p.m. Eastern Time or just have a commitment on Monday nights, hopefully you'll be able to follow along with these videos. So that brings us to Category Theory for Programmers, Chapter 1, Categories. So this is a 9-page chapter, and the first thing you need to know about the book and the author is that Bartosz Milewski used to be a C++ developer, and he became a functional programming convert. So I will put this link in the description of the YouTube video, as I will for all the links. But you can see that from 2012 to 2017, Bartosz gave a number of C++ talks about functional programming patterns and Haskell template metaprogramming in C++. So I haven't watched most of these, but I've heard really, really good things about them. And you'll note from reading through this book that there is definitely a flavor of this is what it looks like in C++, and now this is what it looks like in Haskell. And that's sort of the context that you should be aware of while reading this book. Here is the table of contents for our first chapter. We've got 4 subsections. The title of the chapter is Category, the Essence of Composition, and the first 3 subsections are Arrows as Functions, Properties of Composition, and Composition is the Essence of Programming. The last subsection for all of the chapters will just be the challenges, of which we will always cover a couple. So, as I mentioned, this is a 9-page chapter. Most of the chapters in this book are much shorter than the structure and interpretation of computer programs. Those ones average probably around 30 pages. These ones average around 10 to 15. So these videos going forward will probably be shorter than the SICP ones, although the first one is probably going to be a little bit longer because I have a lot that I want to say and get you excited about this book. So this is the first thing we're going to look at from the textbook, which is actually not from the first chapter, it's from the preface. And it reads, if you're an experienced programmer, you might be asking yourself, I've been coding for so long without worrying about category theory or functional methods. So what's changed? Surely you can't help but notice that there's been a steady stream of new functional features invading imperative languages. Even Java, the bastion of object-oriented programming, let the lambdas in. C++ has recently been evolving at a frantic pace, a new standard every few years, trying to catch up with the changing world. All this activity is in preparation for a disruptive change, or as we physicists call it, a phase transition. If you keep heating water, it will eventually start boiling. We are now in the position of a frog that must decide if it should continue swimming in increasingly hot water or start looking for some alternatives. So this is basically trying to motivate why you should be interested in category theory. Bartosz is pointing out that languages like C++ and C++ 11, we got lambdas. Java 8 in 2014 got lambdas. And there's been a bunch of other functional features that have been creeping into these more imperative languages. And Bartosz is arguing that we are getting to a tipping point. At this point, I want to stop and look at a clip from a Ben Dean talk, which I think, for me, is actually a super motivating quote or reason for why you should be interested in category theory.
To say why this abstract mathematics idea is somewhat important for programming. Because there are people out on Twitter and out in the world who say, mathematics has nothing to do with programming. I'm not interested in finding these abstractions in my code. I just want to engineer the code. To them, I would say, yes, you can program without maths, just like you can bake without knowing any chemistry. But you're doing it anyway. That's the point. Whether or not you know about monoids doesn't change the fact that they are in your code. And so knowing about them should help you to write code. And odds are, if you're a good programmer, you already have an intuition for this stuff. Just like if you're a good baker, you have an intuition for chemistry, even if you're not a chemical engineer.
So to paraphrase what Ben Dean said, category theory is to programming what chemistry is to baking. Whether or not you know about monoids doesn't change the fact that they are in your code. And I think this is fantastic. When I heard this quote, I was sitting in the audience when Ben gave this talk, and I thought it was just awesome, partly because one of my sisters is a baker, and when she was going to pâtissier school, where you learn how to be a professional baker, you learn so much about chemistry. And so when I was talking to her about, everything she was learning, I was like, this sounds like closer to like a chemistry course than it sounds to like a baking school. And it's just so true that category theory implicitly is everywhere in our code. And learning about the chemistry of our baking per se will help us become better bakers. So moving on to the actual content of our chapter, we're starting at subsection 1.1, arrows as functions. The text reads, a category is an embarrassingly simple concept. A category consists of objects and arrows that go between them. The text then goes on to read, think of arrows, which are also called morphisms, as functions. You have a function f that takes an argument of type A and returns a b. You have another function g that takes a b and returns a c. You can compose them by passing the result of f to g. You have just defined a new function that takes an a and returns a c. And Bartosz goes on to show this in C++. It looks like the following, and he's only doing it with type or function declarations for b or the functions f and g. So f takes a type of a and returns a b. G takes a type of b and returns a c. And then we can define a function called g after f, which takes an a and then composes g and f and then returns a c. So pretty straightforward. We then look at the Haskell equivalent of this C++ code, and we have the following: f, which takes an a, returns a b. So if you're not familiar with Haskell type signatures, basically the last thing in this double colon arrow list is the return type. Everything before it is the argument. So we have a single argument and an output b, a single argument b, and an output c, and we compose them just using a period, which is extremely beautiful compared to what we looked at just in C++. And at this point, I want to comment. I think first we should highlight that the book says in mathematics, they usually denote this with a circle. However, it's not built into the prelude that you can use this, but Haskell does support Unicode, so technically you could write code like this. And we should note that the type signature of G composed with F is a function that takes A as an input and returns C. And I want to highlight here that this is known as something in the SKI combinator calculus as the bluebird, which I think is awesome. I'm not going to talk about SK or SKI combinatory logic, but it really fascinates me. And all you need to know is that if we look at the type signature, so the : T on the period gives us basically the type signatures. Haskell has a very, very powerful type inference engine, which can basically give us the type signature of any of our functions. So basically, what this is saying is that composition takes a function that goes from B to C, a function that goes from A to B, and input A, and then returns a C. And this is exactly the Bluebird combinator or the B combinator, what's known as function composition in the SKI combinator calculus. So you don't really need to know about this. I just want to put it on your radar that composition is the Bluebird or the B combinator. So this brings us to our first exercise that we're going to look at. Implement the composition function in your favorite language. It takes two functions as arguments and returns a function that is their composition. My favorite language is APL, therefore we will be solving this in APL. The solution is the following. It's the circle that we saw, the Unicode symbol. So APL actually has a symbol for composition. So what we saw before, that they said, oh, you can do this in Haskell with Unicode, is actually, it just exists in APL. So I just solved the exercise. Hack, life hack. Moving on to the second subsection, 1.2, properties of composition. There are two properties of composition, basically. The first one is associativity, which basically is just rearranging the parentheses around three functions, h, g, and f. So basically, this is just saying that H composed with the composition of G and F is the same or equivalent to H composed with G composed with F. And it shows you what this looks like in Haskell, which is fine. And the second composition is that for every object A, there is an arrow which is a unit of composition. This arrow loops from the object to itself. Being a unit of composition means that when composed with any arrow that either starts at A or ends at A respectively, it gives back the same arrow. The unit arrow for object A is called id, which is short for identity on A. In math notation, if F goes from A to B, then you can state the following. F composed with the identity of A equals F, and the identity of B composed with F is equal to F, or equivalent to F. This brings us to, so basically the identity function just returns you back what you had. So it's basically a no-op, which doesn't seem very useful, but as we work through this book, I'm sure it will become apparent that this is definitely useful in certain circumstances. So the book says that this is what this looks like in C++. We basically have a generic function that takes a generic argument t and then returns that generic argument t. So we're just returning our argument that was passed in x here. In Haskell, this looks as following. So the type signature takes an A, returns an A. The lowercase means it's generic, and we just define this as returning the x that we take in. And note that this function is actually in our prelude. So we can actually just get this out of the standard library that comes with Haskell. This brings us to our second exercise, which reads, implement as best you can the identity function in your favorite language, or your second favorite language if your favorite language happens to be Haskell. As I mentioned before, my favorite language is APL, and therefore we'll be doing this in APL. Identity in APL is also one symbol, which is fantastic. So this is basically a no-op. In the monadic case, when you pass it a single argument, it just gives you that single argument back. I love APL. Life hack number 2. Moving on to our last subsection that isn't the challenges, 1.3, which is entitled Composition is the Essence of Programming. So I'm not going to read this example, but basically this short chapter subsection is just trying to motivate why composition is so important. And the paragraph highlights the magical number 7 plus or minus 2, which basically postulates that we can only keep in our mind 7 plus or minus 2 things at a time. And I actually saw this for the first time in a heard this for the first time in a Rich Hickey talk called Simple Made Easy.
And you know, again, the juggling analogy I think is sound. In fact, the numbers are pretty close, right? How many ideas can you simultaneously keep in your head? It's like 7 plus or minus 2, right? And like the best jugglers in the world, I don't know what they can do, but it's not more than probably a dozen balls. So the cardinality of those two operations is similar.
So that's a fantastic talk. Rich Hickey, for those of you that don't know, is the creator of the Clojure programming language, which is one of the most modern, or if not the most modern, dialect of Lisp, which has got a bunch of awesome ideas implemented in the language implementation. But I actually don't think that the only being able to hold a certain number of things in your head is, at least for me, the strongest argument for composition. For me, it's really the elegance and the clarity in the code that you get. So This is some simple code in C++, pre-C++ 20 ranges that takes a list of numbers, reverses them, and then adds 1 to each of them. So it's very simple, trivial code, nothing special going on here. When you compare this to what the Haskell version of this looks like, because we have composition baked into the language, in my opinion, this is so much more readable. If you juxtapose these two, it's hard for me to hear an argument that C++'s version of this is more expressive. And I'm not saying that C++ isn't a powerful language. Just comparing these two trivial examples, at least for me, it's immediately clear how much more expressive Haskell's code is due to function composition and the composition being baked into the language as a first-class citizen. And if you juxtapose this with the APL solution, it starts to maybe give an idea of why I love APL so much. It's so clear, at least if you're able to read the APL symbols, you know that the circle with the line through it is reverse, and you know that you have to read right to left, that we are reversing and then adding 1 to each of our elements. There's so much more going on in the C++ example. We've got 5 different iterators, 3 begins, 2 ends. You have to be able to digest the lambda syntax and recognize that that's a lambda, whereas in the Haskell and the APL solutions, it's, at least to me, because I can read APL, so expressive and so clear what's happening here. And I just find the two solutions in Haskell and APL so much more beautiful than C++. And note that I'm a professional C++ developer. My day job is writing C++. I'm just envious of the code that can be written in other languages. Not so much the performance, because C++ is a more performant language, but it's definitely more expressive and more beautiful, in my opinion, in Haskell and APL. This brings us to our final challenge or exercise, which reads, write a program that tries to test that your composition function respects identity. So once again, we'll be doing this in APL. This is a little bit hard to digest, as I assume most of you don't read APL, but basically this is a function that takes, test is a function that takes 2 arguments, omega, which is going to be, in our example, a list of numbers or a list of something, and then the alpha is basically a function. So what we're doing here is we're composing our function with the identity function and then testing whether the result of that is equal to just what we would get originally without the composition with identity. And we're applying this using a fork, which is known as an S combinator, also from the SKI combinatory or combinator calculus. But basically what this is doing is it's composing the identity function with our function that we've passed in, alpha, and then that's being applied to omega, and then we're applying just our non-composed with identity function to our input omega, and then it's checking, are the results of those 2 things, our function and our function composed with identity, the same thing. And you can see here we're testing, so our input here is omega is going to be iota 5, which is just a list of numbers from 1 to 5, and the function that we're passing in is reverse. So is reverse composed with identity the same thing as just reverse? And the 1 indicates true. And the second test is a 1 rotate. So we're composing 1 with our dyadic symbol here. That means rotate it in the dyadic case. And once again, when we 1 rotate with identity and 1 rotate without identity on 1 to 5, we get true back. So I love APL, and I hope that you found these answers not super confusing, but if you do find them, we've got solutions already submitted in Swift and a couple other programming languages on the GitHub repo, so feel free to take a look at those. And if you have your own, you can contribute as well by just opening a pull request on the solution GitHub repo. The link will be in the description of this YouTube video. That brings us to the final part of this video, which is just highlighting the lectures that go with the Category Theory for Programmers book that are given by Bartosz Milewski himself. I think they're great. I've only watched the first 2, but they were both fantastic, especially the first one. It doesn't actually tie to anything in the book. It's just setting up the philosophy of category theory and composition and why it's so important. And the lectures do include a lot of visualizations that aren't included in the book, as you can see on the whiteboard. So highly recommend that you go check those out if you're interested. That brings us to the end of the first pre-recording for the coverage of category theory for programmers. I hope you enjoyed. I hope you learned something. If you have any comments or feedback, feel free to leave them down in the comment section below this video. Also, if you enjoyed, feel free to hit that like button. If you think you have friends or colleagues that are going to be interested in following along, either in the live meetups or just with the videos, feel free to share this video with them. Now is the best time to get involved, as we have only just started and we're only 9 pages into this book. So if you know people that might be interested, feel free to share it with them, as there's plenty of time to jump in at this point.